Section: Introduction. In this section, we explore the capabilities of DeepSeek and OpenAI's large language models, LLMs, by testing them on a variety of challenging benchmark problems in numerical algorithms and scientific machine learning. The models we are examining include DeepSeek v3, a general-purpose model trained on a wide range of data, and DeepSeek R1, which is specifically designed for reasoning tasks in math and coding. We also consider ChatGPT 4o, OpenAI's leading model for general reasoning, and ChatGPT 3 Mini-High, a smaller variant optimized for intensive reasoning in science and math. To ensure a fair evaluation, we disable all chat memory and user-specific settings, treating each query independently. We focus on the quality of the solutions generated and the reasoning processes of the models, rather than their response times, which can be influenced by server latency. The test problems we select are intentionally tricky but allow the LLMs some flexibility in choosing methods and parameters for their solutions. Most of these problems are advanced, typically at the PhD level, requiring a solid understanding of computational mathematics and familiarity with recent research. We use TensorFlow and JAX in Python as the coding languages, as they are commonly used in the scientific machine learning community. Our evaluation is divided into two parts. First, we test the model's knowledge in applying traditional numerical methods to solve ordinary and partial differential equations, such as finite difference and finite element methods. In the second part, we assess their performance on scientific machine learning tasks, including digit recognition from the MNIST dataset and the implementation of physics-informed neural networks and deep operator networks for various problems. Section Summary. In this section, we evaluate the performance of DeepSeek and OpenAI's LLMs on challenging benchmark problems in numerical algorithms and scientific machine learning, focusing on their capabilities in traditional numerical methods and advanced machine learning tasks. Our experiments aim to assess the model's reasoning processes and solution quality, particularly in complex computational mathematics scenarios. Section: Traditional Numerical Methods. In this section, we explore the capabilities of four large language models, LLMs, in addressing various numerical methods and solving differential equations. We evaluate how well they generate solutions and the reasoning behind their choices. For the stiff ordinary differential equations, ODEs, we examine the Robertson problem, which models the concentrations of three species over time with specific initial conditions. This problem is challenging due to the differing timescales of the reactions. We prompt the LLMs to implement a numerical method in Python to solve the system of ODEs. The responses from the LLMs are summarized, and we compare their solutions to those obtained using a reliable implicit Runge-Kutta method. We find that the reasoning models, DeepSeek R1 and ChatGPT 3 Mini-High, successfully recognized the stiffness of the system and opted for implicit methods, yielding correct solutions. In contrast, the non-reasoning models struggled, producing unstable results. The reasoning models also provided justifications for their method choices, highlighting the importance of selecting appropriate techniques for stiff systems. Next, we assess the ability of the LLMs to implement finite difference methods for the Poisson equation in an L-shaped domain. We ask all four models to solve the equation with specific boundary conditions using Python. While all models except ChatGPT produced executable code, DeepSeek utilized advanced iterative methods, whereas the others relied on standard finite difference techniques. We observe that DeepSeek R1 made significant errors in both the sign and scale of the solution, while the other models only misidentified the sign. This indicates that while the coding skills of these models are strong, their mathematical accuracy can vary. Additionally, ChatGPT 3 Mini-High demonstrated faster response times compared to DeepSeek R1, leading to more efficient performance overall. Section Summary. In this section, we evaluate the performance of four large language models, LLMs, in solving stiff ordinary differential equations, ODEs, and the 2D Poisson equation using numerical methods. Our findings indicate that reasoning models like DeepSeek R1 and ChatGPT-o3 Mini-High successfully recognized the stiffness of the ODE system and implemented appropriate implicit methods, while non-reasoning models failed. Additionally, in solving the Poisson equation, all models except ChatGPT produced executable code, but ChatGPT demonstrated superior speed and accuracy. Section: Finite element methods for vibrating beam equation. In this section, we explore finite element methods for the vibrating beam equation, considering non-homogeneous boundary conditions. We set the flexural rigidity to 1 Newton per square meter and the length of the beam to 1 for simplicity. The true solution is derived from solving the ordinary differential equation and is illustrated in a figure. We then pose the same question to 4 large language models, LLMs, about using the finite element method from scratch in Python. Our findings reveal that none of the models successfully apply finite element methods to arrive at the correct solution, as shown in another figure. All models utilize Hermite basis functions for approximation, but the non-reasoning models exhibit larger errors compared to the reasoning models, with DeepSeek R1 achieving the lowest error. Next, we assess the ILM's capability to apply quadrature rules for computing integrals with singularities. We ask them to calculate a specific integral using quadrature rules in Python. The models adopt different strategies. DeepSeek v3 directly uses a library for integration, while the others transform the variable to eliminate the singularity before applying Gaussian quadrature rules. Overall, except for DeepSeek v3, the models perform similarly, with ChatGPT-o3 Mini-High achieving the most accurate results by using more nodes. In the scientific machine learning section, we evaluate the LLMs on tasks related to image recognition and physics-informed machine learning. For MNIST digit prediction, we prompt all models to implement a convolutional neural network in TensorFlow. We aim to see how they balance accuracy and computational efficiency. The results show that all models perform comparably in training time and accuracy, with DeepSeek R1 implementing early stopping to prevent overfitting. For physics-informed neural networks, PINNs, we test their performance on solving the Poisson equation with zero Dirichlet boundary conditions in a specific domain. We ask the models to use PINNs in JAX. Only ChatGPT-o3 Mini-High provides the correct solution, outperforming the others. DeepSeek R1 recognizes the L-shaped boundary of the problem, while the non-reasoning models do not. This indicates that reasoning models demonstrate better generalization and responsiveness to user requests. The detailed settings for the models are provided in a table, highlighting that the reasoning model achieves superior accuracy, although it requires more training time. Section Summary. In this section, we evaluate the performance of various large language models, LLMs, in applying finite element methods to solve the vibrating beam equation and in using quadrature rules for integrals, finding that reasoning models like DeepSeek R1 and ChatGPT-o3 Mini-High outperform non-reasoning models in accuracy. Additionally, we test the models on tasks in scientific machine learning, including MNIST digit prediction and solving the 2D Poisson equation with physics-informed neural networks, where reasoning models demonstrate superior generalization and accuracy. Section: DeepONet for learning the antiderivative operator. In this section, we discuss the use of DeepONet to learn the antiderivative operator. DeepONet is a neural operator that helps us understand how to map between different function spaces using data, based on a principle known as the universal approximation theorem for operators. We start with an input function defined on a certain domain and aim to approximate an output function on another domain. The structure of DeepONet includes 2 main parts: a trunk network that processes coordinates from the output domain, and a branch network that takes samples of the input function from specific locations. The output of DeepONet is a combination of the outputs from both networks, along with a trainable bias term. For our initial test, we focus on learning the general antiderivative operator, which transforms an input function into its antiderivative over the interval from 0 to 1. We prompt 4 different language models, LLMs, to implement DeepONet in TensorFlow, ensuring they choose suitable architecture and settings for accuracy and efficiency while being able to generalize across various functions. The LLMs approach the data generation task differently. For instance, DeepSeek v3 generates input functions as random numbers and integrates them numerically. DeepSeek R1 creates data from 4 types of functions, including polynomials and trigonometric functions, calculating their antiderivatives analytically. ChatGPT 4o uses 5th-degree polynomials, while ChatGPT o3 mini-high employs Fourier series, calculating antiderivatives numerically. We also encountered some issues with the code generated by the LLMs. For example, DeepSeek v3 had errors related to tensor dimensions, which we corrected manually. Similarly, ChatGPT 4o mistakenly set the input dimension incorrectly, and we fixed that as well. Among the models, DeepSeek R1 produced the most complex and varied data. However, all models trained for only a few hundred epochs, which is typically insufficient for complete convergence of the loss. To evaluate their performance, we created a universal testing set using functions generated by Gaussian random fields with different scales. We found that functions with smaller scales were harder to predict. Notably, DeepSeek R1 performed well in generalizing to new functions, while DeepSeek v3 struggled to make accurate predictions. Section Summary. In this section, we describe the implementation of DeepONet to learn the antiderivative operator, detailing its architecture with a trunk and branch network, and the various strategies employed by different models to generate training data. We find that the DeepSeek R1 model outperforms others in generalization due to its complex training data, while other models face challenges in making accurate predictions. Section: DeepONet for learning the Caputo fractional derivative operator. In this section, we explore the use of DeepONet to learn the Caputo fractional derivative operator with a fractional order that can vary. The one-dimensional Caputo fractional derivative operator is defined with an arbitrary fractional order, and we denote the first derivative of a function as u prime. We prompt large language models, LLMs, to implement a deep operator network in TensorFlow to learn this operator. The operator maps a function u to a new function s, which involves integrating the product of u prime and a specific term over a defined range. For our test, we sample the function u from a Gaussian random field with a length scale of 0.2. While we specify the input function space, the LLMs are tasked with creating their own training and testing datasets. They must numerically differentiate and integrate the input function, and we summarize their methods in a table. Most models used valid numerical schemes, but ChatGPT 4o made a significant error by integrating over the wrong domain, leading to a division by zero error. We corrected this by using the trapezoidal rule for integration. We are particularly interested in whether the LLMs can correctly incorporate the fractional order into DeepONet, as this order is not typically included in other applications. In the original DeepONet framework, both the fractional order and evaluation points are combined in the trunk network. All 4 LLMs successfully included the fractional order but made a consistent mistake in how they structured the input tensor. They incorrectly paired each evaluation point with a different fractional order, which limited their ability to learn the derivative across the entire domain. As a result, models trained solely on LLM-generated implementations without human intervention showed a relative error exceeding 150%. To address this, we manually adjusted the code to ensure that the spatial input was evaluated at 100 distinct points, with the fractional order randomly selected from a specified range. Additionally, DeepSeek v3 incorrectly trained the model on a single fixed fractional order, despite the requirement for variability. We trained and tested the models on functions generated from the Gaussian random field with random fractional orders. The results, including model architecture and hyperparameters, are documented in a table. We noted that DeepSeek v3 had a high testing error due to its limited training scope, and similar to previous experiments, all models trained for no more than 100 epochs, which was insufficient for convergence. Increasing the training epochs to 1000 significantly reduced the relative error. In summary, we evaluated the performance of various LLMs from OpenAI and DeepSeek on complex tasks in computational mathematics and scientific machine learning. We designed challenging problems that required advanced reasoning and domain-specific knowledge, focusing on the model's ability to select and implement appropriate numerical methods and neural network architectures. Our findings indicate that reasoning-optimized models performed better in recognizing problem characteristics and making informed decisions, while general-purpose models sometimes overlooked specific problem properties, leading to incorrect solutions. This study underscores the potential of LLMs in scientific research and highlights the need for ongoing improvements to enhance their effectiveness in solving scientific problems. Future work should involve more complex real-world challenges to better assess LLM capabilities and guide their responsible use in research.